Welcome to Astronomy Daily, the podcast that brings you the universe one story at a time. I'm Avery.
And I'm Anna. Today, we're journeying from our own cosmic backyard to the vast structures of our galaxy.
That's right. We'll be looking at surprising new data from the moon's far side, a colossal wave of stars discovered in the Milky Way, and an update on SpaceX's next big launch.
And we'll wrap up with a look at the invisible asteroids lurking closer to the sun, a potential threat we're only just beginning to understand. Let's get started.
First up, Anna, let's talk about the moon. We tend to think of it as this static, unchanging rock, but China's Chang E6 mission is telling us a different story.
It certainly is. The rock and soil samples returned from the far side are revealing a fascinating thermal asymmetry. In simple terms, the interior of the moon's far side, the side we never see from Earth, is significantly cooler than the near side.
Cooler? How much cooler are we talking?
Around 180 degrees Fahrenheit or 100 degrees Celsius cooler. That might not sound like a huge number on a planetary scale, but it's enough to explain some long-standing mysteries about the moon's two faces.
Like why the near side is covered in those dark volcanic plains, the Maria, while the far side is so much more rugged and cratered.
Exactly. A hotter near-side mantle would have been more molten, leading to more widespread and prolonged volcanic activity. This heat also explains why the near-side crust is thinner. The cooler far-side mantle solidified earlier, resulting in a thicker crust and far less volcanism.
So the big question is, why? Why would one side be so much hotter than the other?
That's the billion-dollar question. The leading hypothesis is an uneven distribution of heat-producing radioactive elements like uranium and thorium. For some reason, these elements were concentrated on the near side when the moon was forming.
And how would that have happened?
There are a couple of compelling theories. One suggests that a massive ancient impact could have essentially splattered these elements across one hemisphere. Another, more dramatic theory posits that early in its history, Earth had two moons, and a smaller companion moon had a slow-motion collision with the larger one, depositing its element-rich material onto what is now the near side.
Wow, so the face of the moon we see every night might actually be the result of a cosmic fender bender. It really highlights how dynamic and violent the early solar system was. A truly incredible discovery from the Chang E6 mission.
From our closest neighbor to the grand scale of our entire galaxy. Avery, data from the European Space Agency's Gaia space telescope has revealed something truly monumental.
Gaia is always turning up amazing things. What has it found this time?
It's been described as a great wave of stars, a colossal ripple moving outwards from the center of the Milky Way. We're talking about a structure that spans tens of thousands of light years.
A wave of stars? What does that even look like? Are the stars themselves moving in a wave pattern like water?
In a way, yes. This isn't a wave of light, but a literal wave of motion. The collective positions and velocities of millions of stars are perturbed, causing them to move up and down as this ripple propagates through the galactic disk. It's a subtle effect, but on a galactic scale, it's enormous.
That's mind-boggling. A wave that's tens of thousands of light years across? What could possibly cause something that huge?
The most likely culprit is a collision, not a recent one, but an event that happened perhaps a few billion years ago. The thinking is that a dwarf galaxy plunged through the center of the Milky Way's disk.
Like dropping a stone into a pond, but the pond is our galaxy, and the stone is another smaller galaxy.
That's the perfect analogy. The dwarf galaxy's gravity would have punched through the disk, setting off these ripples that are still expanding outwards today. It's a testament to the power of big data in astronomy. By mapping out the 3D motion of billions of stars, we can uncover these hidden dynamics.
And does this wave affect us here in our solar system?
That's a great question. We are likely caught up in this wave, just like all the other stars in our neighborhood. The effect on our solar system's orbit is probably very small, but it's a powerful reminder that we are part of a much larger, dynamic system, shaped by events that took place long before the Earth even formed.
All right, let's bring it back a little closer to home.
It's time for an update from SpaceX. Mark your calendars, because they are targeting October 13th for the 11th flight of the Starship Mega Rocket.
Flight 11. They are certainly keeping a rapid pace. This will be another crucial test for the most powerful rocket ever built. What are the main objectives for this flight, Avery?
The mission profile will look very similar to the successful Flight 10. The main goal is to demonstrate reliability and reusability. They'll launch, the Super Heavy booster will separate and perform a boost-back burn, aiming for a soft splashdown in the Gulf of Mexico.
And the Starship upper stage.
The ship will continue on a suborbital trajectory, coasting for about an hour before performing its own re-entry and attempting a controlled splashdown in the Indian Ocean. They'll also be testing the payload bay door again, this time by deploying some mock Starlink satellites.
Deploying mock satellites is an important step towards the vehicle becoming operational for its primary mission, launching the next generation of Starlink.
Exactly. It's also worth noting that this will be the final flight for the current version 2 of the Starship vehicle. The next flights will feature significant upgrades aimed at even faster turnaround times and greater reliability.
So it's both a validation of the current design and a final farewell before we see the next evolution of Starship. Each of these flights, even when they seem repetitive, gathers an immense amount of data that feeds directly into those future improvements.
That's the key, iteration. We'll be watching on October 13th to see if they can stick the landing, or at least to splash down.
For our final story, we're looking at something that's a bit unsettling: the idea of hitting dangers in our own solar system. Astronomers are suggesting there could be a large undiscovered population of asteroids lurking near the orbit of Venus.
Undiscovered asteroids are always a concern. Why are these ones particularly hard to spot? Are they very small or very dark?
It's neither of those, actually. It's a problem of location. These asteroids are believed to be orbiting the Sun in a resonance with Venus. From our viewpoint on Earth, this means they spend almost all their time in the direction of the Sun.
So they're lost in the glare. You can't really point a telescope at the Sun to look for faint objects.
Precisely. It's like trying to spot a firefly next to a searchlight. Ground-based telescopes are limited to searching the sky at twilight, just after sunset or before sunrise, which gives them a very narrow window to hunt in that direction. This creates a huge observational blind spot.
So we have this potential swarm of asteroids nearby and we can barely see them? Should we be worried? Do they pose a threat to Earth?
The potential is there. The models show that the gravitational pull of Venus can nudge these asteroids into chaotic orbits over millions of years. Some of those chaotic orbits could eventually intersect with Earth's orbit, creating a collision risk down the line.
So this isn't an immediate threat, but a long-term hazard we need to map out. Is there any hope in finding them?
Yes, there is. Upcoming missions are specifically designed to tackle this problem. The Vera Rubin Observatory, with its massive field of view, will be able to survey the sky much more rapidly during twilight. And even better, NASA's NEO Surveyor mission will be a space-based infrared telescope.
A space telescope wouldn't be hampered by the sun's glare in the same way, right?
Exactly. By operating in space and observing in the infrared, where asteroids glow from the sun's heat, NEO Surveyor will be able to find these elusive objects regardless of their position in the sky. It's designed to fill in these dangerous blind spots in our planetary defense network.
That's reassuring. It's a good reminder that the sky isn't empty, and we need to keep our eyes open, even in the places that are hardest to look. And that's all the time we have for today on Astronomy Daily. We've journeyed from our two-faced moon to a great wave in the Milky Way, checked in on Starship, and peered into the sun's glare for hidden asteroids.
It's a constant reminder that there are always new discoveries to be made, both near and far. Thanks so much for joining us.
You can find Astronomy Daily wherever you get your podcasts, or simply visit our website at astronomydaily.io. Be sure to subscribe so you don't miss an episode. Until next time, keep looking up and keep wondering.